we're going to perform 3D finite element simulations in LS-Dyna. For this tribology experiments, or we can say is a rolling contact fatigue based on block origin test. And here you see there is a normal load applied to the pin ranging from 0 to 60 newtons, and the angular speeds of the ring here is the 1400 rpm, and it's running at room temperature. During the experiment, we can measure the temperature where we place the thermocouple near to the pin, and so that we it will be an input to the simulations later on. And also the test sample here for the pin and ring here is from the same material, bearing steel, that is that has 58 HRC in terms of the hardness. And the lubricating agent here, it can be either liquid oil or maybe grease. So here the finite element model. In this case, we have two objects, pin and ring. So the rotation here to the pin, we apply about 1400 rpm. So for these simulations in LS-Dyna, we're going to convert this 1400 rpm into rad over seconds. So using the internet, we can convert it online. We get 146.61, and the ring here we treated as a rigid body, which is non-deformable body, but for the pin here is elastic. The pin is treated as elastic plastic material, so we need to define the stress strain curve of this material. And there is a normal load applied to the pin. And in this case, we go to the next, where we're going to perform the simulation within 10 seconds. And for the normal loads applied to the pin, we're going to replace it with the displacement. So we assume that the ring is displaced from 0 to 2 mm. So it's the same. We can also apply the contact load to the ring, and we can also apply the velocity to the ring going upwards, so it's the same. So in this case, we just want to compare the results between the experiment and the numerical, so it's easy to use the displacement as an input. So the friction here, we're going to apply 0.08. This is what we obtained from the experiments. And ring we treat, as mentioned earlier, rigid as is treated as rigid body. For the pin, elastic plastic material, rotation 146.61 seconds. So we go to the next about the material properties. For the general material properties, here we can obtain the general material properties for the bearing steels from the web. So we got 7,810 kilogram over meter cubed, and the Young modulus, Poisson ratio, thermal conductivity, and specific conductivity. Since we're going to perform thermal mechanical simulations, so we need the thermal properties, and as well as the physical or the mechanical properties of the material. So the top three here is the mechanical, and the bottom two properties here is the for the thermal. And for the elastic plastic, for the pin materials, since the pin is treated as elastic plastic, so we need the effective stress strain curve of the material. So in this case, we're going to use a piecewise material. I'm going to show you later. So we extract the information about the material properties from this paper, from this article. M.U. Abdullah in 2020 is doing the 3D FE model of rolling contact fatigue, published in Tribology Letters. So as you can see in the experiments, in his experiment, we going to extract the sum point here. So for example, 0 to 1800. So about 0.02 we assume is it's not assume, we extract information from here to 2400 and 2400 for 0.04 when the strain is 0.04. So and go on beyond up to the failure point 3050 when it is 0.1. So now let's us try with the finite emissions. So first of all we need to do the solid work. I use the solid work to create the 3D geometry, and then what I need now when I assemble the 3D geometry, so I'm going to import the geometry, the 3D geometry, which I save in the IGES file here. So you can open and go to the SolidWorks, and here the assemble block ring IGS format, and make sure that you choose specify unit mm in millimeter. Click OK, and then now you have it. So if you press Ctrl and press the left button, you can actually rotate this 3D object. So now you see there are two geometry. So we're going to rename this geometry first, so that because easy for us later on. So first we name is pin, and when we pick here, this is ring. Wait, this is ring. Right click, rename, and ring. Okay, now we have these two. So what next is we need to do the mesh. When we want to apply meshing to these two objects, what we need now, we go to element mesh, and since this is 3D, we want to treat this as a solid object. So we choose this solid measure. Okay, the default size here, we see here, we click on default size, is 1.09. we can change it to somewhat smaller. So now we can try with maybe 0.8 for example. So then if we satisfy with this value, so we try with the meshing automatically. It's pretty easy. So let's say if we allow, we agree, then we accept. If not, we're going to reject, and then reject. So now let's say we want it to be 0.7. So we click on try meshing automatically. Okay, now we have it. So I guess we accept this 0.7, and then we agree, we click accept, and now we have it. Okay, as you can see here, we have the object where it is somewhat it looks like a ring, have the color blue of the blue and this color red. Same goes for the pin. So how do we remove? One way to do it, we remove like this. Okay, or the other way around, you just click here. You click this one. You here, since we do not rename this yet, so it is why it becomes solid. If not, we can rename them now. Rename. So ring, and the pin. Okay, so we click on okay, so we go to assembly. So now we have to, okay, now you look here, we can also untick this button. We untick the geometry part because we want the mesh only. So we click to untick, same. So meaning that here automatically untick. So okay, here we click done. So now we have to object. Okay, first of all, when we perform the simulation having contact to each other, what we need to know is that we need to in order to make the simulation successful, we need to introduce a very small gap between the between this contact, okay, before they touch. Okay, so meaning that to move, to shift the object, either one of these object, we need to do this. We go to element tool, we go to move up or to transform. The other way around, we can also use this way. We go to here, FEM model part element tool, we can also choose transform through here. But the easiest way, if you do not familiar with this drop down list, you can also use this button on the right side here. Okay, it's pretty easy with you when you are familiar with this. So you click here. Let's say you want to shift in the Y direction. Let's say you want to shift the pin, so we select the whole pin. Sorry, we zoom out, control, press control, and then play around with the scroll, and then click by part, pick and by part. So the whole object is selected. So we want to move it upwards. So let's say we just want to move up. So we click 0.1. So you see here, there is some small gap. Just here, click +1. So meaning that just click one time, then that's fine. So if you allow this to happen, so just if you think this is okay, just click accept and done. So now let's move on to specify the boundary conditions. We finish with the mesh, and we go to next. We go to here, we click on the create entity. So there are two things you need to know. First is here boundary. Okay, we click here SPC. So we want to create. So first we define we assume that the pin here is not moving at all. So here the pin here is static, so we're going to allow the ring to rotate and move upward, okay, in the Y direction. So Y directions here. So we first we choose this part, the pin, which is not rotating in all directions. It is just fixed in one position. But I think I don't want to do this way. What I need is click clear. So I want to do it again, but then this time around I just want the outer nodes is the one that we going to lock. So we're not going to select by node, pick, and keep going to area. So let's say we choose like this, and going to take some time. This is okay. Like this, like this, like this. So we do not need the entire pin. Oh, sorry. Zoom. Okay, so this is fine. So now let's just see. So what did I select is something like this, only the outer nodes. Okay, so I think that I want to let it fix at all directions. This is XYZ, so no displacement in the XYZ direction. There is no rotation in XYZ direction. So click apply. So the next one is we want to the whole ring here. We select by part. It's moving on the Z direction, right? It's going to Z direction, and also it's going to move up and down. So we allow this to be free in Y direction. So it's free to move in Y direction, and also free to rotate in Z direction. So now then apply. So done, we're done with this. So we go to the show. Since we select this, we click none so that we can untick this selections options. Okay, now we have the node, which is the one we create earlier. So it's better to name them like so with much better name, so that easy for us to detect later on. We click here pin and we click apply. So now you see this is the ring, so we click apply. So we now finish with this. Okay, click none. So okay, the next one is set part. So here we want to create the part. First is pin, so we select here pick by part pin, and then this is pin, apply. And next is we select the ring and apply. Okay, so then we are finished. So here again we go to the show button, we click none so that we not select the objects. Okay, so segment is we're going to use segment later on, but we skip this first. Okay, so now we click on the, we want to specify the boundary condition for the material. So next is we want to specify the rotation here. This we want to input in the value, this value, and also this value. So how to do it? So we go to the model and part. We go to keyword manager, and here we want to assign the boundary, but this is the model, which is the one we chose earlier. So then we go to all, click collapse, and go up and go to define first. Define. Okay, go to define, go to curve. So first we want to ask the ring to rotate. Rotate. Click new ID, and first is 146, right? 0.61 right over seconds. Let's have a look again. Yep, 146.61 right over seconds. So insert, and here we set it to be 20 seconds. It's okay, even though we want to do the simulation 10 seconds. So insert. So now we add SAP, and we see it. See, we have it. Even though we want to run up to 10 seconds, so I recommend you to do it more than that. So maybe you should do maybe 13, 15 is okay, or maybe 11, but not exactly 10. So then the next one is ring to move up. So we call it displacement Y. So now we already click new ID. We have the new ID number 2. And what we need now, let's delete this. So now we want the displacement start from 0 to 0, 0, and then in 20 seconds it's going to displace about 2 mm. So meaning that in one insert, so we add SAP and plot. So meaning that in 20 seconds is going to displace about 2 mm, but then here if we run the simulation up to 10 seconds, so meaning that it will go up about 1 mm only, right? 1 mm only. So it's okay, no worry. We can play around this later on. So we've done with this. So let's say if you don't want to do the displacement, you say that maybe you want it to be velocity. Yes, you can do it. You just specify the value here, velocity, and then it's okay. So you plot the curve here. So you key in the curve and see it. Is it the curve you want it to be? So just define the curve here. So now click collapse. So how to do the Okay, the next one is the boundary. How to do it? We go to prescribed motions, and it is rigid. Since we treated these rings to be rigid, we can also use motion set if we treated this ring as elastic plastic material, but in this case I want it to be rigid. So first, new ID. Okay, new ID is 1. So it's ring to rotate, ring rotate. Okay, we select the ring, and here is DOF. You see, you want it to be to rotate in Z direction, right? So it is number 7. So look again, number 7, right? And then this is what? This is the velocity, acceleration, displacement. So since we are going to apply the velocity to the rigid body, so number 0. So here is ring rotate. So then this is the scale factor. If the ring rotates like this, so let's say you can just the scale factor you can be 1. So let's say you want to double the scale factor, you just put 2 or 1.5 or 3, is up to you. Or maybe you want to change the direction of the rotation, you want it to be clockwise, you just put the minus here. So in this case it is rotating like this, so it doesn't matter rotate like this or like this, so you can put minus or positive, it's up to you. So now done with this, so we click on new ID. Number 2, we want to ring to move up. Displacements. So Y again. See, we use the same name, so we choose the ring again, and here we want it to be translate in Y directions, right? So number 2, and let's say if we want to apply velocity, we choose 0, but in this case we use displacement, so it's going to be 2, this. So rigid body nodes. So again, what is the curve? So we already defined this ring curve is going to be this. So the scale factor here, you can you can double it 2, it's up to you. If you don't want it to be 1, so let's say this is going to move up, so it's going to be positive. So if you want the ring to move down, so you just put negative here. So now we accept, done. So collapse all. Since we want to see the next step is, okay, the next step is we need to specify the ring material and also the pin material. So we need to specify the mechanical properties and the thermal properties. So here we go to material. So first we assign we go to the rigid. We go to number 20 is for the rigid body. So this is for the ring. Rigid means that the body is non-deformable object. So now we click on new ID and rigid, and here you see the density. The mass density here, it depends on this. So in this case here we have the density in unit kilogram meter cube. Since we want it to be if you remember, since beginning we assigned this to be in unit millimeter, right? So we need to convert this into millimeter, and also we want to use the Newton we going to convert this let me just do this. So here as you can see here, this we need to 710 times minus 9. So this one we need to convert 210 times 10's power of 3 10's power of 3 megapascal. So which is megapascal is equal to Newton over meter squared. So meaning that megapascal Newton over meter squared. So this is the one we're going to use. So this we're going to convert into kg over meter cube. So everything here is supposed to be in unit millimeter or Newton or kg. So now we go to a simulation. So here we have 7.81 E minus 9, and here we have 2E 210E3. Here is the Poisson ratio. So mass density, the Young modulus, the Poisson ratio. Here is the, we keep this as a default value, we don't need to do it. So but here, since this is quite important for the rigid body, so now, so this is the case where we want the center of mass constraint in the directions of the, let's say here we going to use this apply to global directions. So we choose one, and the first thing we need to know is that we only allow the ring to move up and down, right? Free to move up and down in y direction only. So meaning that it is constrained in x and z. So we constrain the object. So constrain displacement x and z direction. So it's going to be 6. So next is the second one is the constraint of this is for the rotations. So meaning that is going to rotate freely on the z direction. So it's constrained in xy direction. There is no rotations. We want to constrain this. So here it is x and y directions. Number 4. Okay, now the rest we keep as a default, so accept and done. So we go to the next is there are two ways to specify the material. So the simplest way is to use the piecewise material, this piecewise linear. So meaning that we cut this into the several points so that we have the value for the effective strain and effective stress. So since we have this value, so we can use the piecewise. If we have the, let's say we have the mathematical expression for this curve, stress strain curve. For example, we use Holomon curve. So we can use this one, power law Holomon power law plasticity. So if we have the K and value, the constants, the strength coefficients and the hardening exponents, if we have this both constants value, so it's not a matter of problem. And also sigma y, so we can use this material number 18. But if you don't have it, it's okay. You just use number 24 piecewise linear plasticity like this. Then you just have trying to extract the information from this curve like this. So now we click here is bearing steel. So here we see elastic plastic. Okay, done. Okay, again same value for the density and the Young modulus same value, and the Poisson ratio is also same value. But this is sigma y, we assume it is 1800. And here the strain the material is going to fail maybe at 0.1. Maybe we can extend it to 0.2. It's up to us to decide. So we say that is 0.2 is okay. So the material fail at 0.2. So meaning that since we don't have the value for 0.2 value, so meaning that the simulation here will predict the value where it read the data from the last 2 points and then it project the value. Let me just draw So as you can see here, this is what we call extrapolations. So let's say here up to 0.2, let's say this is the fail, the material is going to fail at 0.2 this point. So meaning that this line here, it depends on the curve here. If it's curvy, it's going to curvy it a little bit and then end. So the material fail at this point, so it will read the value from here. So at this point, this is what we call extrapolations. This is what finite element computation will do during the calculations to get the value. So do not worry about this. So then, so we go to next is we key in the data 0.2, and here CP is we don't touch anything. Here if we have it, the load curve, we can put it. If not, then it's okay. So now look here, we have the, here is the effective plastic strain, here the effective the corresponding yield stress. So meaning that here we have the effective strain and the corresponding stress. So in this case is Z here 1800, 0.02 times 400, 2400, 0.04, 2500, 6, 25, I think here 26, I think here 2750, and this here 0.1, 0.01, 0.025, 0.05, 3000, and lastly 3050 and 0.1. Yeah, this. Okay, now we accept this, we accept, and now we plot to see it. So now this is the curve. So starting from 1800. Okay, done. We're done with this. So now we already have the mechanical properties using for the ring. We treated as rigid, and the pin piecewise linear plasticity. And what about the thermal properties of both materials? Since both materials are of the same material, bearing steel, so we just specify one only for both. So now we go to the thermal. I think here we assume it's to be thermal isotropic. Okay, it's going to be same in x, y, z direction. So that's why we choose isotropic. So we click on new ID for the thermal. Here is the bearing steel, and the thermal. And for the thermal density, we're going to use the same one, E-9. And for the heat capacity, we choose here for 475, and the heat capacity, the thermal conductivity 46.6. I think that's it we need now. So the rest we keep it as default, accept, and done. So now collapse, we specify these material properties, and next is we go to sections. So since we treated both geometry as a solid material, so we go to solid and we click new ID for these solid sections, and here we have many. It's up to us to choose. So we choose default, constant stress, solid element default. So we don't need the rest, we don't need ALE or whatever, we just use the standard one. And here is the temperature, the pressure, and we don't need this, so we just accept and done. So we go to click on collapse. We go to the part. So the part here we already named them with the pin and ring, and what we need now for the pin here, we select solid section, and the material for the ring here is rigid, and here is the equation of state if we have it, and this is for advanced purpose, depends on if it is for the FSI, fluid solid interactions, we can use this. And for the this is the hourglass, so we can also play around with this if you want, but then this is the adaptive options. So let's say if there is this pin undergone very severe mesh distortions, we can use this option where we can create the adaptive remeshings for the solid object, or maybe for the if you perform the 2D finite element model, we can use this option. So for this case we don't need it, so we just use the simplest one. So since there is not a severe distortion to be happens between the both contacts, so we assume that we don't need this. So if it's severe, then we need that. So now the last one is about the thermal properties, thermal material properties. So we already specified the thermal material properties for the bearing steel. We just select, so accept for this. We go to the next one is ring. So we have here section, solid, and done. And the material here we choose the sorry, I think I made mistakes. So for the ring here is the rigid, and the rest is just nice, and thermal here is the same, so we accept. Or just one mistake I made earlier. So the ring is supposed to be rigid and the pin is supposed to be elastic plastic. So go to the pin again, choose this one, and done, accept. Now we check. Okay, so the rest, when we satisfy with this, so we click on collapse, we go to the next. Okay, now the initial condition for this rolling contact fatigue or tribological study to we want to observe what happened is the initial condition supposed to be at room temperature. So first we go to the initial, we set the initial temperature to be at room temperature. That's the most important thing we need to do here. We go to initial, where is it? The initial temperature. So here, not temperature nodes, we want to apply to the set, meaning that to set to both ring and the pin, we not to the specific node. So here we just doesn't matter about this, we just start this at room temperature. Let's say we specify 25 and we click accept. So here we don't need to choose the object, either pin or ring. We can do it, but then it's not important, since if it's 0, it's going to apply to both pin and ring automatically. So meaning that we just accept and done. So the initial is complete. What next is we know that the pin and ring is going to be to make contact, and we need to specify the contact. See, with we need to key in this value, this friction from the experiments. How to do this? We go to the contact. We go to if it's 2D, we go scroll down. We can find this 2D automatic, or maybe one-way surface to surface, or maybe surface to surface. That's what we normally choose. Or maybe if it's we have 2-layer object, we can use tight, or if it's there are many. But in this case, we not to tie them, we not to do the 2D simulation. This is 3D, so that's why we have to go to automatic and surface to surface only. So we just choose this, the simplest one. We click new and the pin ring. So now when we talk about the contact, we need to know that we need to specify which one is master, which one is slave. The first one is the slave and the second one is the master. So normally the ring is the rigid body. So when this ring is the rigid body, so the slave apply to the rigid. So in this case, why we cannot choose this is because of this. This is what we need to specify first. Since for the rigid we can choose the part ID 3. Okay, so we choose ring. Okay, done. And for the master, okay, we choose also part ID 3, and we're going to choose a pin. But the problem here is that this later on I will tell you this, but then we move to the next first. We're going to use a segment later on. So why? I will explain you later on. So first, what we need now, we want to the slave side process also included, and also the master side process also included in this case. And here we specify the friction 0.0. For the static frictions and the dynamic, we leave it as it is. And here is the damping factor. Let's say if we think that the rolling contact fretting having 10% vibrations, we just specify 10. If we have 20% reduction, we just specify 20. If we have maybe about 5%, we just specify 5% vibrations. So but then in this case, we not to assume any vibration. In this case, we say it is 0. So then we satisfy, and the rest we keep it as it is, and we accept. Done. But then the problem here is for the master here, okay, since we expect that when the ring rotates and there is some let me just, okay, when the ring rotates and then it makes contacts to the pin, and there is the contacts, the ring, the node which is closest to the pin will read we find the neighboring nodes to make contact. So let's say if the element here is already deleted due to due to the wear is wear off, so it's going to be deleted. So but then it's going to find the neighboring contact, which is the next one, maybe this element. But then because of the part, we select the part pin as the part object, so it cannot do it. So meaning that in order to do this, we need to assign this pin not as a part, but as a segment. And how to do it? We click done first. We go to element and model and part. We go to create entity, and we go to set segment. Okay, for the set segment here, we click, we're going to create first the segment for the pin segment, and then we click on the entire pin. As you can see, let me just zoom in. You see this. So now the ring, the node that's of the ring that make contact with the pin. So is if one element is already deleted, so it's easy for this node to find the neighboring nodes of the other elements, not only on the surface. So now we click apply, and then we go to show, and then none. And now done. We go back to keyword manager, and we go to automatic surface to surface. We go to here, we choose the master here to be the segment, and we choose pin segment. We click done and save. Okay, so now we already assign the contact. So what next is we want to make the simulation run. We want to run the simulations, so we need to go to control. This is what we normally do. We go to control, so we want to set the simulation to be terminated to stop at 10 seconds, right? 10 seconds. So we can set 12 seconds, 10 seconds, 15 seconds, is up to us. So we go to terminations, we go here, we set 10 seconds, and then the rest we keep it as it is, or we can also play around with this if we want, but then it's okay, just 10 seconds and done. So next is the solution. So here we want to perform the couple, thermal and mechanical analysis, so we're going to choose 2. So if you want to perform the structural analysis only, the mechanical analysis we choose 0, and if we want to perform the thermal analysis only, we choose 1. So in this case we choose 2, and then the rest we keep it as it is, default, except done. Okay, now this is the explicit we're going to run the simulation using the explicit mode, not implicit. So if it's implicit, you choose implicit auto and implicit solution and implicit general and implicit solutions, if I'm not mistaken. If it explicit, you just select solution only. Okay, now about the thermal, we need also to perform the thermal simulation, so that's why we choose thermal solver, and we need to choose this as a transient. And for the p type here, the thermal problem type, we say is going to be 1, since it's non-linear problem. It's not gonna be non-linear. And for the A type, thermal analysis type, we just choose transients, and the rest is we keep it as it is, and then we accept done. And now we go to contact. When we finish with thermal solver, we need to go to thermal time steps. This is very important. So let's say if we want to do the fixed time step, so we choose 0 default, and here we can use fully implicit or maybe cranky Nicholson schemes default. And here we can specify also the initial thermal time step if we want, but in this case I want it to be variable time steps, and here we choose the implicit, okay, for the thermal. And for the initial, here we say, let's say we 5e minus 1e minus 5. Okay, so for the initial time steps, we click accept, and we finish with this, and I guess we click done. So next is about the contact. We also need to turn on this one important informations. We need to gather this information about we want to ask the simulate this LS-Dyna to calculate the frictional energy when both this pin and ring make contact. So we click accept. So we can play around with this scale factor, so that we allow the nodes when of the pin and ring, which is to penetrate each other. Maybe master penetrates about in a small just go into the element of the pin a little bit, so we can play around with this. But then I recommend you to put it as default if you do really not needed this need this to play around this. So we just need to ask this simulation to calculate only. So now collapse, click collapse, and now we want to ask the LS-Dyna to create data for us. So to do that, you go to database, you go to binary D3 plot. Okay, so here we can say 0.02 for example, and the rest we can just keep it as is. You can just choose this whatever, but then the rest I keep it as a default 0.02. and then for this we can also extend the binary D3 plot. How to do it? We go to extend binary. We go to the binary. If we want to ask the string we want to ask the LS-Dyna to write the plastic strain data to D3 plot, we can just choose one here. If we don't want it to be like that, it's okay, we can. We don't need this, but in this case I don't want this, so normally I will choose the extend binary, but sometimes you don't need it. But in this case, okay, here you choose the default, the time interval 0.01, and then click enter. So it's gonna apply to all of the data. So now what kind of data you want to extract from the simulations? So let's say you want to read the elements output data for all element, for example. So normally I will choose this, not force, nodal force group, nodal displacement, velocity, accelerations. So meaning that the nodal point H is nodal. So here also resultant interface forces, resultant, and also we want to read the temperature value. So we choose this, and the rest we keep it as it is and accept and done. So now collapse, we already finished with this. So I guess we just need to save this. Save. So we don't need to save this as a IJS. We go to here. Okay, we just see at block on ring, or maybe rolling contact fatigue. So this is the K file format, and save. Now let's check. So we have here. Okay, now we run. How to run this simulation? We go to here, launch manager. So here we want to, if we want to create another the prepose LS prepose, we click here. But for this, if you want to run these simulations, what you need to do is we go to the server, start the LS-Dyna analysis, or you just simply click this button, start LS-Dyna analysis. So browse the file. We go to this here and click run. And now let's look is the simulation okay or not? Is there any problem? It's going to take a longer time. I already prepared the simulation for you. So as you can see here, it's going to take very long time, 7,000 hours 20 seconds 20 minutes 26 minutes. So meaning that it's going to take very long time. So what you need now, okay, let's not waste our time. So assume that we already have it. This one I run it with a default mesh element size with 1 mm. So the one we did this. This is the mesh element size is around 0.7, right? So but then this one is okay. So now go to start LS prepose. It's going to take very long time. But there is no problem with the simulation, don't worry. Yep. Yeah. This. Oh. let's say we stop this simulation since it's going to take very long time. What we need now is I want to show you how to extract deformations. So here you see the let's say here I have the other simulations which is successful, and you click on the D3 plot and then you drag this to the LS pre-post. So now you have it. So you see these simulations happen. So it's starting to make contact. So if you want to make it faster, you just click on here. You increase the incremental time here to 5, for example. So now it go faster, way faster. Or maybe you want it to be 10. Now it go much way faster than. So now you see it move, right? Okay. So maybe 5. We just want to see it move, and then at the same time, okay, it's okay. Let's say we stop here. We keep. Okay, now I want to show you how to extract the information. So let's say here we have we want to see the y stress. So you see the y stress value. So let's say you want to see the von Mises, though this is the von Mises. So this is the temperature. So you see the temperature is around 43. Let's see if you want to read the displacement, for example. I think the y displacement, you can see it, the displacement. Okay, and the velocity also we can see it, this velocity. But the one we want to read here is the thermal. Okay, and the thermal. So let's see if we can move this to the left, and then we remove this ring. So at this time interval, for example, we want it to be at 250, for example. And so this is 200 only, for example. So now we have this. So just assume that you want this information, and at 200 maybe we just okay, now 54. Okay, it's okay. Now we click on, let's say we want to change the background to plane, for example, to plane. Okay, so we can just use the snipping tool, and we go here, we just cut it like this, and then we create copy, and then we have this one here for the results. So now we have it. This is the temperature reading at time 2 time steps 200. Okay, let's say we want to read the von Mises. So here we have it, von Mises, and copy and paste. And now we have the information, so we can compare side by side like this. Or let's say we want to read what else. Since the strain value is gonna be very small, we go here, so we have the strain value. The strain value also here, but then since the strain value is very small, we just choose the infinitesimal strain. We choose effective strain, and then we go to here, we just click here, and then we have this one. Now right click, copy and paste. Now we have the strain, just to make it smaller so that each one can be put together. So now we have the temperature, the effective stress, the effective strain. So now, yeah, like this. So I'm going to show you next how to extract the information. So we change it to feed. Okay, so just assume that you want to you see that the effective stress, for example, here not satisfied with this, so you want to compare, you want to have a standard value, so a standard fringe range, the range value. So you choose user here. Let's see here the value, maybe you want to change it to be 2, or let's say we choose temperature lah, mudah. So temperature, so we go to the his, we go to user, sorry, wait, this is temperature. No, this is not temperature. This temperature is very low in temperature value. There's something that is not. Oh, maybe something wrong. Suppose we can read the material. I see we choose dynamic done. Okay, so we have, let's say we want it to be the maximum is 80, for example, and sorry, the maximum is 80, the minimum is, for example, 25. So let's say here 100 lah, for example. We just 25 and 100, for example. So we just click enter. So now we have this value. So if you do not agree with this value, we can just always modify them. For example, 80, something 60. Okay, 60, so meaning that the rest is okay. So it's difficult. So since it's okay, so if you want to play around, you can also use this. Okay, we cannot detect, so let's say, just let me try one more time. Say 85. Okay, so it's going to happen to the rows, to the whole part. It's okay. Okay, so we just choose dynamic in this case, but if you want to use a user, it's also possible. So okay, next is the how to extract information from the history, and then we can do the plot for the XY. But in this case, we going to use this together with the Microsoft Excel. So we click on here. So here you have the reading for the global point. So the global okay, you have the kinetic energy and whatever, but in this case I want to read the nodal. The nodal, you can choose the nodal and read the temperature. It's also possible. So if you do, let's say you want to choose this part and then this part, and then you want to read this part here, so you try to click plot, then you see the reading. Yep. So let's click here. So let's say this node, you plot, so you have the reading. So if you can also choose the element. So in this case I want to show you the element, so we choose one element. So let's say the element we choose is exactly at the center, for example. So just one element. Let's say we turn on the ring. So the ring we read from the side, for example, not from the side. Okay, so there's one there. So okay, see that, right? There's one. So we want it to be, let's say it's something not right. Okay, let's say we choose this one, the one at the center, and the one that we assume that is going to distort severely. So we want to read the temperature of that material, for example. So where is it? Yeah, this. We click plot. So we click here save, and we browse. So it's going to save in this case here. So we click here plot and temp, and we're going to save it into txt file. So save and done. Quit. And now we want to read, let's say, resultant velocity. So maybe y velocity, the velocity in y directions. So you can also read it, or maybe the x velocity in x directions, we can read it. So let's say velocity. So here you see the velocity in x directions. So let's say we want to read the displacement in y direction. Click plot, and it reads 4 nodes actually. So in this case it's okay, not a big problem to us. We just have the temperatures here. We have the displacement y, dash y, and we save and done. Quit. Okay, now we go to the Microsoft Excel. We have the data. If we go to the file, you have the plot here. We click here, we have the file, we save in txt file. Why did I save in the txt file? Because we can use MATLAB to read this these informations, or we can also use the Microsoft Excel. So in the Microsoft Excel, you click here open, and then we go to the browse, and then we go to the desktops. Here we go to the file. Okay, in this file we click here all file, and you scroll down, we have the displacement. We read the displacement. Okay, so we go to the next, but then this do not split into two. Go back and we choose the fixed width. We go next. Okay, now we have two. Finish. Now we have two columns. So this is the time, and the time in unit second, and here is the displacement y in unit millimeter. So the rest we don't need this. Okay, now we have the information about this. We want to open the temperature. Same, we choose fixed width. Next, okay. Copy, and then we put it here. We have the time here, we have the temperature. in unit degree Celsius. Okay, now all this data supposed to be in, we change it to not scientific, general. So we have the time reading is same, so we just change these locations, cut and insert there, so cut, and we don't need the time anymore, we delete. You see the displacement here is okay. So now we plot the data for these two, temperature as function of time, and here we have insert and plot. So you see, this is, so we have to now, this is the temperature degree versus displacement y. Right, in unit mm. We can also have another graph where this one versus time, second, and also we can change this data, this to be there, time, we set time. Okay, now we go up. Now here, oops, this is the time, temperature as function of time, temperature as function of displacement. I think that's it for now. Thank you so much for listening to this recording for this 3D finite elements model in LS-Dyna for this ring compressions block on ring task, so or rolling contact fatigue. So thank you so much